We continue our session, and the next speaker is Gleb Nenashev, who will talk about Schubert Calculus and bosonic operators.
Yes, okay. Thank you for this opportunity. I would like to be here. Thank you all organizers. And I'm glad to be the only speaker from Russia. Let's start. At first, my talk about Schubert Calculus and bosonic operators, but the reason for this is that you can work with Schubert Calculus without any knowledge. And at first, I will show this for similar. Of course, a lot of you know about Littlewood-Richardson coefficients, and I will present definition of them without anything. And so it is what I will do at first. Okay, so it's a Young diagram. So 4, 3, 1, and I'm working with just vector space of Young diagrams. So we have finite sums of Young diagrams with rational coefficients. And so Kirov defined the following two operators. One is increasing, where we add one box to Young diagram with some coefficient, and we take this diagram with this coefficient, and operator down, where we delete one box and again with some coefficients. J minus I corresponds to column index minus row index, so it's constant. This operator was defined by Kirov, but first place where you can read this in Akunkov's paper. Z, it's just some parameter, so it's. But so as you see, so D, it depends on Z prime, and so we can consider split this operator into two. So just D, where we have only constant, J minus I, and Xi, where you take diagram with coefficient 1. Okay, and let's present example. So this Xi, we just delete all so boxes in all possible ways, such that it's still a Young diagram. And D, we take some coefficients. So here we coefficient 4 minus 1, so it's first column and first row. Here 3 minus 2, so it's 1. And here 1 minus 3, so coefficient is minus 2. And so here's important lemma. At first, by 1, I denote empty diagram. So it's some confusion, but 1 is empty diagram. It's similar as x in power 0. It's usually 1. So empty diagram is 1, and element from Qy is constant. So if and only if both operators give 0. So we have such lemma, and it's easy to prove. It's just combinatorial fact. So you need to consider good order of some lexicographic order of diagrams, and later you will prove this. It's not so hard. And from this lemma, we can get following corollary. What? So X is a sum of some Young diagrams. And if both operators give 0, it means that we have only empty diagram. Okay, and from this lemma, we immediately can get that there is only one pseudo multiplicity. So what is multiplicity? Multiplicative map. It just, we need that it's bilinear, graded. So by graded, we mean that if we consider product of diagrams with 5 and 4 boxes, in the product we will have only diagrams with 9 boxes. And also two more properties for C and D that this multiplication satisfy Leibniz rule. Okay, and from KLM it's immediately that there is at most one multiplication map, but in fact there is exactly one, and its multiplication is just similar to, so these coefficients will be Littlewood Richardson coefficients. And you can assume this as definition. So, and good point, usually for define Littlewood Richardson coefficients, you need either representation theory, either cohomology for Grassmannian case, either Schur functions, or you will define via some tableau or puzzles, but it's only combinatorial, but not as multiplication. And but here you can see there is one profit that you don't need to know even what is polynomial. So it's multiplication, but I didn't use polynomials. Okay, but let's show another example of this theory. So I want to prove a Jacobi-Trudy identity. It's very simple in this notation. Okay, HL is just a strip of L boxes. Because we have unique multiplication, it's automatically commutative. So, because otherwise we can swap. Okay, let's prove this formula. Yes. How we can prove this? By induction, of course. And to prove this, we need just to check. Okay, assume that we check base, and now we need to only to check induction step. And for this, we need just to prove that Xi of left hand side equals Xi of right hand side, and same for D. Okay, how we can prove for Xi? So Xi of H has very simple formula. And let's combine everything by row, combine by rows, and we get that. So for Xi, we just need to remove one from index. So, and when we is from first row, it's we change lambda 1 to lambda 1 minus 1. Is we change lambda 2 to lambda 2 minus 1, and etc. And in fact, if it's became not Young diagrams, determinant will be 0. And when it's still a Young diagram, it means that we deleted one box. And it's what we need because this by induction step is holds. Okay, and same, almost same for D, but now D of strip has this strange coefficient, but we need split it into two parts. The first lambda I minus I, and second j minus 1. And now we combine this again by rows, and we will receive this stuff. And when we combine this by columns, we get that if we add minus 1 to this column, we receive previous one. So determinant is 0. And when we put here minus 1 everywhere, our coefficient is also 1 minus 1. It's 0. So it's proof of a Jacobi-Trudy identity formula. Okay, there's more for Schur case, but now let's speak about Schubert. So this is a classical definition of Schubert polynomials, or some people can say that it's theorem by De Mazur or Bernstein, Gilfan. So what we need? We define from longest permutation. So for permutation n minus 1, etc. 1, and later we use divided difference operator to define for other permutations. And definition is correct no matter how we receive a shorter permutation. Okay, but this definition is correct even if so. Okay, 1 second. Sn is by natural way is included to Sn plus 1. and this definition is correct after this. So we can assume that Schubert polynomials is well defined for permutations of all natural numbers, fixing all but finitely many elements. Okay, and Schubert polynomials, linear basis, it's easy to check because again, if we consider good order of some good order, then we will get that leading terms of all Schubert polynomials are distinct. So it's definitely linear basis, and they are all possible. So we can get that it's the product of two Schubert polynomials is sum of another Schubert polynomials with some coefficients. And it's a big combinatorial problem to give interpretation of these coefficients. Okay, what is problem here really? For Grassmannian case or Schur function, we have representation theory and cohomology ring. Here we don't have representation theory. And in fact, for Grassmannian case, it's there is no good transfer from representation theory to cohomology ring. So just we know that it should be same, but it's not really that we can theoretically show. And by this, in this problem, exactly happens that all interpretations of Littlewood-Richardson coefficients based on really on representation theory. But here we don't have representation theory. We need work only with cohomology ring. There is some interpretation as intersection of some stuff. You can guess that it's 3-point Gromov-Witten invariance, but it's not really good because we have interpretation, but you cannot compute coefficient structure constants with these interpretations because you need some to solve something, and it's impossible. The only way to compute these Littlewood-Richardson coefficients is just from accept some special cases from this multiplication, and during these computations you will have minuses. So it's not, and it's not good when you compute in positive integer numbers with minuses. And really, this is really old problem, and so far it's still open. Okay, but some special cases are known, and the first one is multiplied by simple transposition, and it's Monk's rule. It's from 1954, and it's you need just multiply. You will have sum of permutations multiplied by some transpositions. You need that length is increasing exactly by 1. Length is number of inversions in permutation. Yes, so this formula, and you can rewrite this using operators AB, and just use such operator, right? 0 if otherwise, and this Schubert polynomial if length increasing exactly by 1. This operators AB, you can see it in Kirillov's talk, so in talk in the morning, and Kirillov denoted this by UAB. There's a few more rules. It's Satil, where we multiply by HK, a complete homogeneous symmetric function, and it's just such formula. And for elementary symmetric functions, you have this formula. And there's a few more cases, but okay, I will write. There's also a rule when you multiply by Schur functions for hook. There's rules for this multiplication, and it's almost everything. Because for other rules, it's only special permutations here, or restrictions on both permutations, which is not really good. And all these rules from beginning of 90s. So it's really old. So no new rules in last 30 years.
So that one is positive as well.
Yes, yes. What? Julian Xatil also in same paper. It is from same paper as these two rules, but it's harder to formulate, so I don't want to do it. Okay, and let's speak a bit about recent. So Schubert polynomials are polynomials. So we can consider such operator D as a sum of all partial derivatives. Of course, it satisfies Leibniz rule for free, but also it has a really good formula. And it's coincide with this curves operator. Let's go back to Schur functions. Schubert polynomials for some permutations are exactly Schur functions, and for this we need just permutation is Grassmannian if it has only if it's increasing except one place. So for example, permutations 5, 2, 5, 7, 1, 3, 4, 6, it's increasing except place 7, 1. And if you rotate your head, you can see here Young diagram. 4, 3, 1. And it's what is written here. And Schubert polynomials for such Grassmannian permutation, it's exactly Schur function. Okay, and operator D is coincide in this notation. So D of Schubert polynomials is D of such Schur function. But you know that in Schur functions you have infinitely many variables. And so far in each Schubert polynomials we have only finitely many variables. And it's not problem. There's two stabilities of Schubert polynomials. The first we consider just shift of permutation. It sent a simple transposition sk to sk plus 1. And by permutation you can construct another permutation by this way. And Stanley symmetric functions is just when you apply this tau infinitely many times. You can see the limit. And backstable Schubert polynomial is when you do same thing, but now you also shift variables. We add negative variables with negative indexes. And Stanley symmetric function defined for all permutations of natural numbers, but now backstable Schubert polynomials defined for permutations of all integer numbers, including negative. Because after some shift, you will have permutations only of natural indexes. Okay, a bit about Stanley symmetric functions. Stanley symmetric functions is sum of Schur functions. And all coefficients are non-negative integer numbers. There's some interpretations, one you can read here, but it's really not big deal for this talk. There's also another interpretation in a recent work by Lamley and Shimazona. Okay, and you see here again interpretations using some tableau. Okay, another stuff from paper Lamley and Shimazona that backstable Schubert polynomials is a linear basis of some stuff, and again we have some product. This and here we have new structure constants, but they are not new. They're exactly the same. But now all structure constants indexed by 3 permutations of integer numbers, but we have this shift, and by shift it's equal. And using shift you can get all permutations from natural numbers here. And in this case it will be exactly structure constants for usual Schubert polynomials. So if you solve this problem, you will solve original problem and vice versa. So it's equivalent problem. But there are some pluses here. But at first, let's define operators, Xi and D. So now Xi, we just multiply by Sk simple transposition on left if length is decreasing by 1 with coefficient 1. And for D, we have coefficient K. Note that now in this we can get negative coefficients because K can be negative. It satisfies Leibniz rule. And what is true for backstable Schubert polynomials and not true for Schubert polynomials, this equality. That if Ru is number of reduced words, we can get this inequality. We need just apply Xi a lot of times. We need to apply operator Xi a lot of times and we will get this equality. For example, if we multiply these two Schubert polynomials, we have this Schubert polynomial. And if we multiply these two Schubert polynomials, we have this two. And as on the picture, so it's a wiring diagram for left-hand side, and this is a wiring diagrams for right-hand side in this sum. So this is a wiring diagram for this permutation, and these two wiring diagrams for these two permutation. And here we don't have this one. We have only this. Okay, and as you see, here someone really want to construct multiplication rule as just merge two wiring diagrams and just move intersections and to get this. But it's what really people want, but it's no one did it yet. Okay, and another that there is no other operators except of Xi and D with such property. So if we have operator eta which send Schubert polynomial to Schubert polynomial when we multiply on Sk left if length is decreasing. So and if it satisfies Leibniz rule, then eta is linear combination of Xi and D. So, and it's what happens. So for Schur functions, we have two operators, and they define everything. For Schubert polynomials, we again have two operators, and we don't have third one. And it's not problem, they define everything again, even for Schubert case. But we need a bit. So there is unique graded bilinear map star such that for any two permutations, identical times identical is identical. It's again bilinear. So if we multiply permutations of length 5 and 4, we will have only sum of permutations of length 9. It satisfies Leibniz rule for Xi and D. And one more property which is not really necessary, but here we need a bit, that if all coefficients are non-negative integer, then there is unique such graded map, bilinear graded map, and it's exactly structure constants for Schubert polynomials, for backstable Schubert polynomials. But instead of this condition, you can write almost anything. So, for example, another type that now we write that it's U times V belongs to such. So here we attend. Here in the product we have only some permutations, not all. So we just restrict all. So here is just true, but I'm not sure that it's really interesting now. So it's yes.
Sorry, if you just relax the fourth condition, so what kind of, so how many binary maps are there?
So if you delete condition 4, you just say that product of two Schubert polynomials equals to product of their Stanley symmetric functions. So, but no, you can send product of two permutations to product of Stanley symmetric functions. And so it's even if you times 1 times u, you will have such only sent to Stanley symmetric functions. So it will be automatically. Yes. In the proof you don't need, but you will receive that you have associative, and of course it's commutative because it's unique. You don't need to understand this C. If it's unique, it should be associative and commutative. Okay, these two criteria, positive, support, and here it's still weak, so we can write stronger theorem, but I will say later about this. Okay, let's show how to prove Monck's rule using this technique. Just D is sum of operators dk when we multiply by sk on left. And mz is just this Monck's rule which we really want. Dk and operator AB are almost commute because dk acts on left side of permutation, AB on right side of permutation. And they are not commute except cases when UA, UB is exactly k and k plus 1 in some order. And so we can write this, that D and MZ almost commute. We receive this, and the rest when UA and UB from different sides of some number, and it's exactly here. We have coefficients, and you can check combinatorially that it should be exactly 0. And so it's equals this. So proof of Monck's rule is very simple. And in fact, let's say a bit in another direction. So from Monck's rule, you can prove C and D. Exactly reverse proof. And what it means? That to work, so when you understand everything, now you can just forget about paper by De Mazur and Bernstein-Gelfand. Because we have Monck's rule. It's from 1954. Then you have C and D. Then structure constants are unique and you define it everything. Now you can work. Paper by De Mazur and Bernstein-Gelfand are not necessary anymore. But also even to prove a divided difference operator from C and D, it's also not hard. So it's definitely the shortest way how to prove divided difference operator. Okay, let's speak about a bit about bosonic operators. Oh, I have a lot of time. So operator rho 1 is just C. And what we have that C and D just multiply by simple transposition on left. And usually these operations are almost commute. If we multiply by Si and Sj on left, if I and j indexes, difference of indexes at least 2, then they commute. And so it's a very natural way to consider commutator of these operators. And it's what we did. Rho 1 is C and rho k plus 1 is commutator of rho k and d divided by k. And so it's here. And if you have two operators which satisfy Leibniz rule, then this commutator is also satisfied. So we have for free is here. And also I proved that these operators are commute pairwise. And because I have a lot of time, let's back to theorems, to these theorems. So we know that if C and D satisfy Leibniz rule, then rho K satisfy. But in this theorem, instead of this rule, you need just check rho K for any K, for all K. Maybe it's harder because you will have infinity, but formally it's a bit less. And here again, you can change D to rho K. Okay, and combinatorially, you can prove that rho K of this, it's just when you delete border strip. So it's dual Mordna Nakayama rule. So what is border strip? It's when you delete such stuff. You delete some snake. So, and to prove this, it's very combinatorial, and I'm not sure, maybe here it's not -1. I always confused about this because height of one box is 0. Yes, it should be without. Yes, it's some strange notation. So, okay, but now because we have operator C and D, we have dual Montgomery-Nakayama rule for Schubert polynomials. Before we didn't have this, and for Schubert polynomials, I was lazy to write. But coefficients are still plus or -1. No 2, no 3, no, just plus or -1 or 0. And some condition for permutation. Okay, but okay. Yes, very similar. So it's just generalization. So I can draw a wiring diagram for this permutations, so in which you can multiply on left. Okay, and now because we have operators rho, we can define even more operators xi lambda. We can define xi lambda as some character divided by z mu and product of these operators. They commute, so it's not problem. Okay, and the product of these operators have a Littlewood Richardson coefficient. It follows because it's same as for Schur functions. It's the first part, it's not big deal, but the second it's more interesting because now we have this Hopf structure for operators. And the third condition is that when we multiply by this operator xi, we will have this coefficient from Edelman-Green interpretation of Stanley symmetric function. So these A lambda U are coefficients from Stanley symmetric functions. So these coefficients are non-negative integer numbers. Okay, and again, in these theorems, instead of to check by xi and d, it's enough to check just xi lambda for any lambda. You will have more operators, but they are linear combination of xi and d. Not linear combination, but some polynomial of xi and d. Okay, and another important stuff which I should say, but maybe it's clear, that in these theorems, instead of permutations from U and V, you can restrict second on smaller class. For example, you can try to prove using these theorems to prove that U times any Grassmannian permutations. So if you can formulate similar theorem when if you have such stuff, bilinear graded map, graded bilinear map, when U any permutations and V is Grassmannian of descent M. If you formulate such theorem, it's still true, and it can help to solve case Schubert times Schur. and it's what is it? The case Schubert times Schur is still open, and usually every year or every second year someone announces that it's solved, but later people find mistake. The last stuff such happens in 2023, so in last year. Okay, and I think it's everything what I wanted to say. Thank you.
So any questions or comments?
Uh-huh. Yes. But not for complete flag variety. Yeah, but it will be for sure case. No, no, I don't know this. Sorry. I will see. Thank you for question. So far, I don't know.
Any more questions? Okay, then maybe a short question from me. You started, you say that Akunkov spoke about this initial operators
Road,
Dipakirov
yes.
because of the connection with the Z measures.
It's on my slide, yes.
So if we now turn to Schubert case.
Oh, no, because for measure you need really up operator. So to define measure, you need not only down operator, you need operator up when it's increasing.
Mm-hmm.
But for Schubert, you have only down operator, unfortunately.
Mm-hmm. Okay, thank you.
So.
And so we define these operators in such way just because to produce a measure in some way. So that's motivation or definition or what. So why we define them in this way? So what's the profit? Just because we like studied from it and then like forgotten.
So it's repeat please again. I didn't hear how.
So why we define these operators in such way? So what they give us? What they give rise to?
Okay, but so it's just when I started work. Yes. So at first I define it at first operator C, later find operator D in literature for Schubert, and later found this for Schur functions. So my motivation is not related to Schur functions at all. So, but it was natural. So when I started with C, I understood this property, and it should be somewhere later. No. So it's operator D. Sorry. D limit. No, it's okay. Yes. So when I start to work, I just found this equality, and it wasn't known before, at least in literature. So, and some experts didn't know this. So it's from Xi. So for Xi, it's really natural because Xi you can also write as in terms of variables. It's also just limit, which is even more natural than D. It's more natural than D. But motivation, for me, motivation was to solve product. But of course, I didn't do it. Maybe yet, maybe never.
Okay, thank you.
Yeah.
Any more questions? Then let us thank Gleb again